Welcome, everyone. The first thing is, if you have a question about Zoom, you may email me at acecontra@stevens.edu. If you were dialing in with a question for our guest, we'll address those. If you have a question for our guest, please use the Q&A feature. The chat feature is also available for any other questions or comments. We will try to get to every question today. If not, we will forward them to our guest to try to get an answer afterward. Today's talk will be recorded, and we will send it to you via email, and it will be up on the SERC YouTube page. So before we get to our guest, I am pleased to welcome our technical moderator. He is the Executive Director for the Systems Engineering Research Center and the Acquisition Innovation Research Center. Please welcome Dr. Dinesh Verma.
Thank you, Alan. As we transition over to Myron Hecht's slides, just a couple of minutes to give you a sense for his background. It is, first of all, a real pleasure for me to welcome Myron as one of our speakers on the SERC Talk series. He has a fascinating background with degrees in science, engineering, business, and law. I believe all of them from UCLA. I don't believe we've had a speaker with that varied a background, since the SERC Talk series started under Dr. Barry Bame's leadership. I also wanted to let the audience know about the relevance of Myron's talk. His research interest is in system reliability, maintainability, supportability, security, safety, and hence you can imagine makes him a natural to talk about perhaps application of SysML methods and techniques for system certification. It was with that topic in mind that we reached out to Myron, given the research he's done in this space, and grateful that his schedule allowed him to be our speaker today. Over to you, Myron.
Thank you very much, Dinesh. Can I be heard and seen?
We can hear you loud and clear, and we can see you, Myron.
Okay. The second challenge now is, can you see my charts, which I hope we will be able to do very soon. All right, so share. All right. Pardon that little bit of confusion there. I will be talking today about how SysML can support certification. Here is the agenda. We'll first of all define what at least I mean by certification. And then I'll speak about three approaches to how SysML can be used in doing certification. And they're listed here. And then finally, I'll have some concluding remarks. So first of all, what is a certification? Everybody has a different definition of certification, and it does have various meanings in different contexts. For example, you might be asked to certify that your publication is in fact yours, and that doesn't involve a certification agency. Or you might get a certified letter from the US Post Office. But when we speak about certification, at least in this context, I'm going to use the ISO definition, which is the provision by an independent body of a written assurance that the product, service, or system meets specific requirements. And since we're talking about SysML at this point, we're talking about systems, not product, not services. So everybody who has a need for certification probably has a particular agency from which that certification is required, and that's often defined by legal requirements. If you're trying to certify an airplane, then you'll go to the FAA. If you want to allow a commercial operation of a nuclear reactor in the United States, you go to the Nuclear Regulatory Commission. If you're a DoD entity and you want to operate a information system, you need an authorization to operate from a DoD cybersecurity authority. So those certification authorities generally require some kind of evidence to show, well, first of all, they'll set forth a set of requirements, and then they'll require some kind of evidence that their requirements have been met. And this is frequently, those requirements for what requirements they have and how they are to be met is often set forth in standards. For the DoD, in system safety, there's MIL standard 882E. In the automotive industry, it's once again for safety, it's ISO 26262. In the aviation industry for software, it's DO 178C. And for nuclear reactors, once again for software, it's IEEE 603, et cetera. So that's the game. You meet the requirements of the certification authority, and they give you a certificate often in written form, but in some kind of persistent form that you can then present to others to show that your system meets their requirements. So that's been going on for decades. The question is, how can SysML help to do that? And the first approach that we're going to show is to use SysML unmodified, if you will, out of the box. And how would that work? Here's the simple 10-step process for doing that. First of all, you would want to input or ingest the certification requirements into SysML and make them into SysML requirements. Then you'll want to define the verification methods, once again, in SysML for each of the requirements. You'll have to do that in any case outside of SysML, but we want to model them within the SysML model that we're building. Then within the model, we'll want to locate the relevant elements of those, of how those requirements are to be met. Generally that's system blocks. They could be activities. Then the idea, the next step, and this is the important one, is to allocate the certification requirements to those model elements, primarily blocks, as I've mentioned. And then a very important step is, once you have requirements, how are you going to show that they've been conformed with? So those are the verification methods. And then we go to the capabilities of the tools, not necessarily directly part of the SysML language, but the two tools I've had most experience with, which is the now Dassault Cameo System Modeler and the Sparks Enterprise Architect, have the capability of creating traceability matrices. In Cameo, it's called dependency matrices, to show basically the mapping of the certification requirements and the verification objectives and the components. And then with all of that, once you have that traceability, you can start talking about generating a certification plan, which basically will answer two questions. What do I need to test for each component in the system to show conformance? And the other thing is, how do I demonstrate conformance for each of the requirements in the certification activity? And then show that plan to the certification authority. We're now back into how it's done, whether or not you have a model. Execute the plan, once again, outside the model, and then submit the evidence to the certification authority in the format it requires. Now, go through some demonstrations of this. This is requirements that have been imported into SysML, into what's called a requirements table. These happen to be requirements from a standard called AFMAN 91-119, which happens to do with software used in nuclear weapons. But what we have here is a simple list of requirements. This doesn't look too much different than what you would have seen on paper, but in fact, each one of these requirements is an object within the SysML language and can be manipulated in ways that you can't just do on paper. So you can have additional fields. You can show relationships. And let me show you what some of those relationships are. Well, let me first speak about the verification objectives, which also have to be defined. These are basically how each of the requirements will be satisfied. In some cases, you have many to-one relationships. You could have many verification objectives for a specific requirement if it's a complex requirement. Or on the other hand, a single verification method might satisfy or might show conformance for several requirements. But let's speak about what you can do with SysML requirements and particularly how they're going to help in certification. Going back to our nuclear weapons example, the top level requirement coming from an Air Force instruction 91-101.3 is that there shall be positive measures to prevent inadvertent pre-arming, arming, launching, or releasing of weapons in all normal and credible abnormal environments. That's a pretty broad requirement, and so what we need to do is we need to break that down, and that's broken down in a number of ways. But in the domain of software, one of those requirements would be memory protection. That you have to ensure that erroneous data in the processor of that nuclear weapon doesn't cause an error, doesn't affect any critical component or function of that weapon. Excuse me. And then we break that down even more into something concrete, and we have a requirement for variable initialization. Now, we now have a set of concrete, feasible requirements that we can work with. And the first thing we need to do is decide how we're going to allocate that requirement. And we show here, let's see if I can get a laser pointer. If I can.
Myron, we can see your cursor.
Oh, you can see the cursor? Okay, fine. Excellent, thank you. So we allocate them right here to the, I wish I could move my cursor. We can allocate them to a software element called OFP, which happens to be Operational Flight Program. And for those of you who know SysML or UML, in SysML, these are called operations. In UML, they'd be called methods. But the OFP has all of these functions, and all of them will be satisfied by, or this requirement will be satisfied by all of these requirements. We'll want to be sure that we have that the variables are initialized. Now, how are we going to verify that requirement? Well, we're going to verify that requirement through a watch point or a breakpoint in a debugger, where we can see that all variables are initialized before they're being used. So we replicate this for all requirements and all components in the systems for which those requirements are allocated. And then we end up with tables such as these, where we have basically allocations, requirements on the rows, and the system elements to which they've been allocated in the columns. And we satisfy ourselves that there are no empty rows and no empty columns. And we also show this to the certification authority, show that we have complete coverage. Then we can create tables such as these. These are one table here shows which components have been, or what requirements have been allocated to which components, excuse me, which is shown here. So for this, it's the arming and fusing assembly, and it has a number of requirements that have been allocated to it. And each one of these requirements has a verification method or verification objective. And we can do the same thing, for example, listing requirements instead of the items to be tested in the first column, so that the certification authority can review and see that all the requirements have been met in the system. Now, one of the things that we can do in both in major modeling tools is get the information out. So here we've gotten the information out in the in the form of a Word document. This Word document was generated automatically by querying the model to get the relevant elements in accordance with, at least in Cameo, using a language called the Velocity Template language, which happens to have been developed for websites, but which was adopted for Cameo. And then you can create something like this, and you can also create those tables. Now, the advantages of this method is that the applicant uses the capabilities of SysML and of the tool to produce the documentation. This can be done on demand. So we don't have to freeze the design at some point, maybe 6 months before we submit the document, and say, you can't make any changes. We're going to start documenting this now, because if you make changes, then the credibility of our whole certification application is lost. So we get consistency between the certification documentation and the actual design with the automated document representation. And the certification agency doesn't even have to know that the documentation was produced in a model. It gets its Word or PDF documents in exactly the same form that it's always gotten them in, and they can use their own internal processes to do that. Well, the disadvantages are that the what we're representing in the model is, of course, only in the model. I can allocate a requirement to a component, and show how it's going to be certified, but I can't actually do the certification within the model. I have to actually perform the certification externally. And the other thing is that these approaches to generate documentation automatically is tool unique. It's not specified in the language. And that means that if you start in one tool, you're kind of stuck with that tool for further duration in order to produce the documentation. And of course, the model and the documentation are not portable among tools. Okay, let's move on to our second approach, which is using a profile to extend SysML to a specific domain that you'd be using in the application. And want to clarify what a profile is. A profile, once again, is a term that has a lot of meanings in different contexts. what we mean in SysML and UML is to tailor the SysML to a specific purpose. And what that means is, first of all, that you have to really define what the purpose is. So you'll create something called a meta model, which is often an ontology, so that you can define precisely what you're doing. Then you'll add features to the language, which are the ones indicated here, stereotypes, tags, and relationships to make the language unique, basically to add features to the language so that it is more closely aligned with the objectives. And then you finally might add some constraints so that you don't, with all of the stereotypes and relationships that you create, you don't, there might be some limitations on that. So after you've done all of those, you've basically enabled queries to be performed, and those queries are called views in SysML. And so you can produce diagrams and tables for displaying new information, and you can understand how that would be important to a certification authority. And then finally, to create templates for the exported artifacts, all of the tables and reports that might be needed by the certification authority, similar to the first method. So the profile, as I mentioned, the primary element is the ontology or meta model for identification of key elements and relationships. Then if you will, concretization of those of that meta model into the language using these concepts of stereotypes, tags, relationships, and constraints, and then creating views into the model, and then producing the artifacts, as was mentioned earlier. A simple example to show how profiles work, and in order to do that, I just created a meta model of a local area network. And I say that a local area network has nodes, and each node has an address, and each node has a property tag, some identification of what it is, some serial identification, and then a location where that network asset is. So with that very simple meta model, we can create stereotypes. And we say, well, what does a network node really have? A network node has two kinds of addresses: a hardware address, the MAC, and the network unique address, which is called the IP address. And then we have a stereotype of location. Well, what's a location? A location is a building, a room, a rack within the room, and a slot within the rack where the asset might exist. And then we have finally for the property ID, we have just an inventory number, which we give as a string. And then we apply those stereotypes based on the model that we've developed. So, for example, here's the network node. We have the address and the location here in the meta model, and finally the property ID. Then we can start applying those stereotypes actually to our network assets. Here we have a server, a workstation, and a router, which are part of the network. And we can now, with our extensions, take a regular SysML block, which is the server, and add these stereotypes so that we can now show within the model where that server is located, what its address is, and what its property number is. Now, you might say, if those of you who know SysML can say, well, I can do that in a block anyway. Why do I need to do it with stereotypes? Well, the point is that we have a block for a server, we have a block for a workstation, we have a block for a router, and we can apply the same properties of location, property ID, and network node to all of these elements. And that's basically the advantage of doing this. When we move into the certification realm, let's just say system safety, these cross block properties might include things such as risks, hazard IDs, mitigations, and some kind of verification status, so that we can then keep track of how well we're doing in our system safety certification program. And so speaking of system safety, this is a model that we published for MIL Standard 882, which in SysML, which enables the application of what can be a very complicated standard, and in a large system, very difficult and overwhelming to implement, and make that more tractable. So what are the key elements? First of all, within MIL Standard 882, there are a number of tasks which have to be performed, various kinds of analyses. You see H and a lot of those acronyms there. So that's a hazard, PHL's preliminary hazard list, PHA's preliminary hazard analysis, and so on. Then we have, so that's a key element. We have to perform these tasks. Then performing these tasks involves basically collecting information. So we have a hazard element, and we created this, what we call a super hazard element, which is a simple record, which is going to be collecting a lot of data as we go through the various analyses about each one of the hazards. And then we are going to be producing subsets of that large block in terms of system safety reports. Now, within that system safety data, we have a number of items such as a risk, and a mitigation. And when we have a mitigation, there might be multiple steps to that mitigation, and we call each one of those a mitigation measure. And then we have some other elements like the system safety organization, the actual design, and we also have some other concepts such as workflow and process progress tracking that's done by the system safety organization. I don't want to go into this meta model in more detail, but that gives you an idea of what it is. And given that meta model, we can then, go on and produce these types of reports. And they're in the form of tables. One is just the listing of the hazards, and that's important for the hazard list and the preliminary hazard analysis. Another table is risks. That's not required specifically by the system safety report, although they do require a rating of the hazards in terms of what the risks are, but they're certainly important to the program management as well. Then we have mitigations. We want to show how we're mitigating these hazards, reducing their severity or the likelihood of their occurrence, or preferably both. And then another program specific property, which is how well we're doing and progressing in mitigating these hazards. And we can produce that information also in tables. Now, these are tables within SysML. they can be exported to standard Microsoft Office type documents for a presentation to both program management and the Safety Certification Authority as needed, and as was discussed in our first native SysML case. Now, these are some of the exports that we get from that model. The system safety risk matrix for each one of these hazards. You're familiar with them. The basically traffic light, green, yellow, and red indications of the hazards. Then we might show how the risks are being burned down. And these are model templates, exports that were created within the profile. And these templates can be exported as we noted earlier. And for example, here is that risk matrix, and we're showing the burn down plan. And all of the information was contained within the model and was produced using the export capability, this velocity template language from Cameo. And just the system safety risk matrix without the burn down plan. And here we have one of the standard outputs of the MIL standard 882 task. This is the system subsystem hazard analysis, and it results in the SSHAR, the hazard analysis report. And this was also generated from information within the model and was produced in this format for a safety certification. The safety certifier doesn't have to know anything about how this this template was produced, and the system safety organization can wait until the day before they have to the deadline for handing it in to generate it and allow progress to be made and not impede any aspect of the program, simply because they had to freeze the design in order to produce these documents. Okay, so the advantages of doing the of adding the profile is that you can really make things more efficient. You can and this doesn't only matter for the structure of the model. It also reflects the way in which people communicate, because now by adding terms such as hazard, risk, which don't which are not native to SysML, but by adding them, all of a sudden the modelers and the domain experts begin to communicate. As information is added, and this is going to be added by the system safety engineers as they go through the model and update the information, just as they would be writing things down in notebooks or typing things up in reports. But now it's all being done in the model, so that at any point you can get up-to-date information and get the certification authority documents on demand. And as noted several times, and this is really important, I think, the certification of the agency may or may not have any modeling expertise, but they certainly do know their domain, and they want the information in a manner that they can understand it and review it. So it's very important that it be produced in a manner that they can expect. Now, the disadvantages is, once again, the certification is being performed, or the model can describe the certification activities, but the model doesn't perform them. And creating profiles, I think you can imagine how much work went into really refining the concepts and revising them and coming up with the right relationships. It's not simple. And it's more complicated by the fact that the domain experts are not used to thinking about ontologies, and the modelers are not used to thinking about the domain, so it requires some work. And as mentioned with the first approach that we came about, documentation is generation is not portable. So you choose a tool and you have to live with that throughout the life of the certification effort. Well, the final approach that I want to talk about was use of the model itself. This is fairly limited. It's not been done much. With the introduction of a new version of SysML called SysML v2, I think the opportunities are increased, but let's talk about it a little bit. What we have in SysML tool v2 is what's called a formalized semantics. And what that means is that there's a language which has been used to define the SysML language. And that language, which is called the kernel modeling language, fondly known as kernel, enables us to really speak about very specifically what the relationships and what the elements in SysML mean. And because we can do so in writing very precisely, we can analyze it. And you don't need too much semantics when you're talking about a block, but when you're talking about the relationships among elements, what does something before something else mean? Or what is something, a time occurring interval within certain constraints? That turns out to be very important in temporal analyses, and wasn't well defined in SysML v1. It wasn't defined as all. And so within SysML v2, you do have precise definitions for those properties, and that allows you to begin to do analysis. Now, SysML itself, v2 doesn't have any capability to perform those analyses, but there are many formal methods, tools that have been created to do those analyses extrinsically. And in the past, what's been done is that the analyst has had to represent the system in some kind of a language, and then that language can be processed to determine whether the specified properties indeed exist within it. That's typically been the stumbling block to prevent application of formal methods in system models. And while those languages still exist and the analysis tools on those languages exist, and they've been around for decades, we now have the possibility of doing a translation because of the precise semantics. And that's what we're showing here, where we have the SysML v2 tool. The features needed for each of those languages is extracted using something called a plugin, which is, you can think of it as something like a dynamic link library in Windows, where you just, except it's not dynamic, it's static. You add it, and it customizes the software of the tool rather than the language used by the tool. And you can extract the features that you need, and then feed that information to each of these formal method systems, depending on the methodology you're using, contract-based designs, model checking using finite state machines or linear temporal logic, and actually perform a verification on the model. And here's an example from SysML v2 using contract, where we have a assertion which defines the properties to be satisfied. That's the assumption. And then the guarantee is what the behavior of the model element is in order to satisfy that contract. And by doing so, you can perform the operations of contract analysis, assumption guarantee contracts, using a tool such as Agree or such as Okra, which was developed out of an institute, FBK, in Italy. I think that's La France. I'm sorry, I forgot what the name of the institute is. But this work has been going on in Okra. It's been going on for decades. And now they've been able to apply it to SysML v2, which I think is going to be a big step forward to enabling formal methods, which is, of course, important for certification. There's another type of certificate use of the model for self-generation of artifacts, and that's work that we've done on failure modes and effects analyses, where we actually use the properties of SysML v1 to create networks and of failure propagation paths, and then define how those propagation paths can be changed, and or how those failures can be transformed as they propagate through the system. And then we create reports of those propagations, each one of those propagations in various ways, and that turns out to be exactly what a failure modes and effects analysis is. Once again, the model enables that to be done quickly and automatically. Now, the advantages of this approach is that certification can be performed on the model, and as with the other methods, it allows tracking of certification requirements and conformance. But unlike the other methods, which would require manual insertion of the information, here the model inherently provides that information. So it can be done on demand, it can prevent up-to-date information, and so that's a real step forward. The disadvantages are model-based certification methods are still at the research stage and not widely used. SysML v2 is still not formally approved and released. Prototypes exist. A lot of work has been done. It's thousands of pages, so it's pretty much done, but the final OMG processes have not yet been executed. It does require substantial expertise, and requires expertise not only in the SysML modeling language and in the model itself, but also in the formal verification methods. And this is not widely known. There has to be an agreement with the certification authority that particular formal method can be used to satisfy a requirement. And finally, the big one, certification in the model is not the same as certification of the system. You can have a behavior that's specified in the, excuse me, in the model, but you also have to show that the system has that same behavior. So for some concluding remarks, what conditions would you have to have in order to have successful certification using SysML? First of all, the applicant has to have the capabilities to do SysML model-based systems engineering. You have to include all of the requirements and verifications within the models, and you have to be able to produce the certification artifacts in the form expected by the certification authority. Now, what does the certification authority have? First of all, although I've made the claim several times that the certification artifacts can be transparent, the certification authority doesn't need to know that they were generated by the model. I think the certification authority will want to know that there's a model there, and will probably have some requirements on those models. The certification authority might want to verify that the artifacts, in fact, do represent the model. So they would want to have their own analysis capabilities and tools, and they would have to have an evaluation process for looking at what those results or what the output of those tools are in terms of whether it's accepted. There has to be agreement between the applicant and the certification authority. And that typically would happen with a model-based certification plan, which would identify what artifacts and evidence are necessary, the acceptance criteria, how they would be evaluated, and then most importantly, how the plan could be modified in the course of the development. So my concluding comment before opening up this discussion is, does anybody know of any model-based certifications that are occurring? I don't. But if there's any audience that would have that information, if somebody's aware of something or is actually performing a pilot in model-based certification, I'd sure like to know about that and maybe introduce that to the group. So with that, my talk is concluded, and let's take some of the questions in the remaining time.
So Myron, I'll use your question as a jump-off point for an initial question, and there's some questions in the Q&A that are related to this as well. In your mind, what is likely the holdup with an organization wanting to be the first to go through this notion of a model-based certification?
Well, I think the problem is that becoming good in SysML requires time, and it requires learning. And many people have to have that that level of knowledge. You wouldn't go into any kind of software development process using people who have had several weeks of training in the language and expect that that's sufficient. So that ultimately the competence within modeling languages, and particularly within SysML, is necessary. Secondly, I think certification authorities, by their nature, have to be conservative and always looking at precedents and always looking to get approval from their own stakeholders. One way to lose your credibility as a certification organization is to certify something and for something to go terribly wrong. So there is a inherent conservatism, and that can be overcome with experience. But it's kind of a vicious circle where if you don't have the experience, how are you going to not become conservative? I mean, the way you do that is iteration, and you work it out, and you start with simple examples, and you gain confidence, and then you proceed. But it takes a while to get that process started.
So, yeah, a related question from Chris Hoffman is: have you addressed, or have you seen others address, the skills gap and the need for collaborative modeling? For example, for configuration management of the model, for non-typical modelers, for example, system safety engineers or reliability engineers, in the same data set as system modelers?
That's a big problem. But that's dealt with in the processes and methods within the particular organization. one of the things that you want in a repository is always to have the ability to go back, so that if somebody makes a mistake, or you want to know all of the changes that a particular suspect person made to a model, you can find those. And model repositories that I have experience with have that capability, so that you can keep track of changes. The other thing is, of course, you limit access, and you only allow authorized people to make changes to the model. You might want to expose that model to a wider framework, a larger audience of people. And I don't know what Sparks has, but Cameo has this capability called the collaborator, which is the ability to comment on a model, which has been lacking until now. So these aren't people who are allowed to edit the model itself, but they can alter. There's like an additional layer of things that which commenters can alter without affecting the model itself. The other aspects of this, and particularly in a project environment, is making sure that the pieces that the individuals are working on can be integrated and that there's interoperability. That's once again not unique to certification, but it creating the standards within the program or within the model of how things are to be modeled, and what interfaces have to exist at the edges of models, and what common data models are going to be drawing from has to be defined. That's a separate area, which is in itself fertile area for I'm not sure it's research, but it's research, I guess, certainly development of how we do that effectively. We've learned how to do that over the decades in software development, and the capabilities that we now have for tools, everything from Bitbucket to Jira to the static analysis tools to DevSecOps and what we get with all of those capabilities took a long time to develop, and we'll have to do the same thing. We'll have to undergo that same cycle of development in SysML as well.
So Myron, Ken Craig asked a question, then proposed a response too. His question is, how would you validate the model and the system? And what might be the practical use of such joint validation? Would a strategy be to run the model and the system with sensors feeding both to validate that the model and the system behave correctly and consistently? Your thoughts on that?
Well, that's the dream of digital twins. Ideally, that would be a wonderful thing to do. And we should bear in mind that SysML models are system engineering models, and they're not mechanical engineering models, and they're not software models. So we only get down to a certain level of detail within the SysML model. So we might know what the acceleration of a vehicle is, but we might not know anything about what's going on in the engine of that vehicle to know that the engine is still within conformance, or what went wrong if we're not in conformance. So I wanted to make that point, which digital twins doesn't limit itself to SysML models. But ideally, yeah, we would want that. And, it would be nice to be able to achieve that. The problem in digital twins and integration is that the truth is that the sad truth is that the developer of one three-dimensional CAD system didn't really develop it in order to be interoperable with other software.
Yes.
And not only that, but they don't particularly want to make it interoperable. because that would destroy their competitive advantage, at least within their market. And you know, we look at what used to be totally disparate applications for spreadsheet processing and for word processing and for drawing, and they're now incredibly well integrated. When I say that incredibly well, I mean to the point that we don't even think about the fact that we can cut and paste things between Word and PowerPoint and Excel. But what it did was it took one vendor who enforced common standards among all of their departments, developing those individual tools to enable that to happen.
Yeah.
And we don't have that yet in the world of system engineering or engineering more broadly.
So Myron, I'll ask one more question. Given that we have a couple of minutes left, I'll pick the question from Jason Langley. His question is, has this approach been applied successfully on agile development, systems engineering programs? And if so, do you have any advice on how to minimize rework of certification planning when a greater awareness of the overarching system operation is realized post-assessment of subsystem elements in specific sprints?
Rework within Agile is a outcome of poor planning or poor execution. Maybe poor is not the appropriate word to use. Incomplete planning, or people don't finish their meeting the objectives at the end of their sprints. And I would say that certification falls within, or rework during certification would be the causes for why that happens would be no different than the reasons why a particular user story is not satisfied at the end of a epic. And it's once again a topic in and of itself for how do you execute agile development in a rigorous and disciplined way, and is it still agile if you enforce, if you have to plan so heavily, or is it really more like a modified waterfall? And
I understand.
I'm aware of those arguments, and I've probably gotten some people alienated by what I've said. And if so, I apologize. It's not really my area. It's just something I've observed.
No, really appreciate that, Myron. Myron, let's close it at this point. We're right at about 1 o'clock. Thank you so much for preparing these slides and these messages for us and the audience. To the audience, I'll say you'll be hearing from Alan and the SERC team. You will have access to this briefing as well as Myron's slides. Over to you, Alan, for any last-minute logistics.